continue with aromaticity, let's look at some other examples of aromatic compounds. We call them heterocycles because they contain heteroatoms, which is oxygen, nitrogen, and sulfur. These can also be aromatic. For example, the first heterocyclic aromatic compound we are looking at is pyridine. Again, it's heterocyclic. It's a heterocyclic structure because of the presence of nitrogen, which is one of these elements listed here that qualify a ring to be called heterocyclic. So you see the structure looks very similar to benzene. Now we also have a lone pair. So if you are not careful, you would say you have 8 pi electrons, the 6 in the pi bonds and the 2 out here. But that's not going to be true because these 2 electrons don't play part in resonance. In fact, the clue is whenever you already have a double bond onto the nitrogen or an oxygen or a sulfur, you don't use any extra lone pairs to do resonance. You only use the pi bond, okay? As a general rule. So if you are to count the pi electrons, there are 6 pi electrons here. And then obviously it's a ring. You see this resonance, this conjugation, all elements are sp2, including the nitrogen is sp2 because you have 3 electronic groups, the lone pair, the double bond, and the single bond. So you predict that every atom center is trigonal and flat and planar. So the last rule you want to check is 4n plus 2 rule equals to number of pi electrons. Of course it's 6 pi electrons, and n will be solving for 1, not a fraction. So yes, this guy is aromatic. It passes all the 4 rules. It's cyclic, it's conjugated, it's planar, and it passes 4n plus 2 rule, just like benzene. My emphasis again is on those 2 electrons. They don't take part in resonance, so don't say there's 8 pi electrons. And it's shown right here. Those 2 electrons are on the same plane as the ring. The electrons that are above the ring are the only ones that are delocalized. They move around in resonance. That's what delocalization means. They move around in resonance. Okay, so you can count 1, 2, 3, 4, 5, and 6. Remember, 2 of these will make a pi bond, 2 of these will make a pi bond, 2 of these will make a pi bond. That's why we have the 3 pi bonds in the ring. The lone pair, this lone pair right here, occupies the sp2 hybrid orbital perpendicular to the direction of the 6p orbitals. So they are 90 degrees apart. That's why they don't take part, these lone pair electrons don't take part in resonance. The other heterocycle is called a pyrrole. Now you see how this nitrogen does not have a double bond. That means we have to use these 2 electrons for resonance. If I push this here, this can be pushed there and this can be pushed here. Obviously the double bonds have moved and you get resonances using the lone pair. So you have the 2 pi bonds, which will give you 4 pi electrons, and then you have 1 lone pair of electrons, which gives you 2 electrons. In total you have 6 pi electrons, and for that reason, again, this molecule passes the 4n plus 2 rule equals to number of pi electrons, which is 6 pi electrons, 4n plus 2, so 4n equals to 4n equals to 1. It also passes rule number 1, 2, 3, because this is rule 4. It's a ring, check. It's conjugated, I can draw resonances around, check. Is it planar? The answer is yes. This nitrogen is still sp2, even though one would think that you have 4 electron domains, that you have a lone pair and 3 single bonds to make 4 electron domains. That's not true. You cannot count the lone pair as an electron domain because it's going around the ring. It's not available to be counted. Instead of being called as an electron domain, it will be counted as pi electrons. So you are left with the 3 bonds, which makes 3 electron domains because the lone pair is not available to be counted, and the hybridization has to be sp2. So every atom center is trigonal planar. These carbons have hydrogens on them, remember that. So they have 3 electron domains all around. That makes the ring overall flat. So it passes rule number 3 of it. Of course, we showed it passed rule number 4. So the p-ρ is cyclic, planar, completely conjugated, and passes 4n+2 rule. It's therefore aromatic. The lone pair this time, as compared to the pyridine, where the lone pair was on the plane of the ring, the lone pair is on the top, so it will be able to take part in resonance. Like I pushed arrows here, so you have 6 pi electrons. Okay. Next is we just talked about the p-ρ and mentioned how this lone pair is on top to make 6 pi electrons. So next is the furan. Okay. One of the lone pair will be on top of the ring, the other will be on the plane on sp2 hybrid orbital. This will be on the p orbital. So if you have to draw it in 3D showing the electrons, this is what you'll see for the furan. One will be on top, one will be on the plane. So the red ones are the 6 pi electrons, and the black one is actually sitting in the sp2 orbital, meaning the black lone pair does not take part in resonance, only the red one. Okay, and you're gonna have 6 pi electrons. These two guys are aromatic compounds because, again, if you have 6 pi electrons and the molecule is cyclic, planar, and conjugated and passes 4n+2 number of pi electrons, then that molecule is deemed to be aromatic. Okay, the kind of shaded brownish orange color just implies the delocalization of the 6 pi electrons. That qualifies rule number 4. So, question, which of the lone pair nitrogens can take part in resonance and in aromaticity? I gave you the clue. If you're seeing a double bond bonded to the nitrogen, then any lone pair that's present will not take part in resonance because it's occupying the sp2. But this nitrogen right here is not doubly bonded to anything, so I am able to use the lone pair for resonance. Like I could push that one there, push this one there, push this one there. So which of the nitrogens can participate in resonance? It has to be this, because it's not doubly bonded to anything and it has the lone pair. So the answer is that. Okay, that lone pair can take part in resonance because it's nitrogen, it's not doubly bonded. Next question, which statement is true about thiazole? These are thiazole because it contains a sulfur and a nitrogen. This is imidazole. This one right here is called imidazole because it contains the nitrogen. This is thiazole because of the presence of the sulfur. Now look at the sulfur. It's not doubly bonded to anything. So one of these lone pairs will take part in resonance. Let me assume that this lone pair is on the p orbital, and then this one will be taken to be in the sp2. So only the one in the p orbital will take part in resonance, simply because the sulfur is not doubly bonded to anything, and I can push the electrons around. This lone pair here will not take part in resonance. It's in the sp2. Obviously, I gave you the clue that if the nitrogen or an element is doubly bonded, if the heteroatom element is, if the atom of the hetero element is doubly bonded to another element, then you consider the lone pair sitting on that element not to take part into resonance. So it's just going to be in sp2. So the only lone pair that will take part in resonance will be one of these lone pairs on sulfur. So which statement is true about thiazole? A, both lone pairs of sulfur contribute to the pi electron clouds. That's false. Only one of the lone pair will take part, the one in the p orbital. One lone pair on sulfur contributes to the pi electron clouds, and the lone pair on nitrogen does not. That's correct. This does not take part in resonance. Of course, it's sitting on an element, nitrogen, which is doubly bonded already. And one of that will take part in resonance, like you said. One lone pair on sulfur and one lone pair on nitrogen will contribute to the pi electron. Nope. Nitrogen will not. The lone pair on nitrogen contributes. Nope. The answer is B. So here are other examples of aromatic compounds listed. So we've already described that. We've talked about the furan, we talked about pyrrole, we talked about the pyridine, we talked about the benzene. Now let me talk about these ions. So whenever you have a cyclopentadienyl anion, you see that's a carbon right there. So if I'm to draw the electrons into D, I am tempted to put the lone pair up there, and that's okay, that's correct, because I know that my carbon right there is not doubly bonded to anything. So I can use the lone pair as part of resonance. So if I'm to count, I see I have 6 pi electrons. Now, what is the hybridization of this carbon? If the lone pair is taking part in resonance, like we've determined, because the carbon there is not doubly bonded to anything, let's see, this will end up here. So if the lone pair takes part in resonance, then we're gonna count it as part of the pi electron count, and that means that I do have 6 pi electrons, and so that qualifies the fourth rule, which is 4n plus 2 equals to number of pi electrons, which will solve for n equals to 1, not a fraction. So this compound is cyclic. Of course, everything is sp2 hybridized. The lone pair is taking part in resonance, so I only have 3 electron domains, the 3 sigma bonds, 3 single bonds. So it's sp2 is trigonoplanar. If it's trigonoplanar, everything is planar. The ring is small, it's conjugated, and it's cyclic, and it's qualifying this rule. So I'll call this aromatic. That's why it's listed as examples of aromatic compounds on the title of the slide. So here I do have a hydrogen. Now I can push this here. This can come there, and this can come there. Alternatively, I can push. Let me change the color. I can do resonances the other way around, where this can go towards where the electrons are lacking. This will fill in the gap created by the first bond, and this will come here. See, there's resonance all around, and this carbon right here is sp2 hybridized. The rest of the carbons are sp2 hybridized. I expect the molecule to be trigonal, to be planar, because all carbon centers are trigonal planar molecular geometry, have the trigonal planar molecular geometry. So it's a ring, check. It's conjugated, check, because I can do resonances, and then it's planar, check, because all carbon centers are sp2s with trigonal planar geometry. And the last rule, I see I have 3 pi electrons, 3 pi bonds, which means I have 6 pi electrons. So which means if I try to solve for n will turn out to be 1. It's not a fraction, so it checks out. Tropylium cation is aromatic. Next, we have this structure right here. You see, I can do resonances going this way to that carbon, or I can start from the bottom and do it this way. Right? So either way, I can do resonances with all those carbon centers, so it's conjugated. Now, you should realize again, we have hydrogens not shown. If these lone pairs can be used for resonance, they are not counted as electron domains. So I'm left with 3 sigma bonds on each of these negatively charged carbon. So those carbons are sp2s. These carbons bearing the negative charges are sp2s, meaning they are trigonal and planar, underlined planar. Obviously, these other carbons are sp2s, they're trigonal planar. The whole molecule is flat. Now, if these lone pairs are taking part in resonance, I'm counting them as pi electrons. So I have 4 electrons in the 2 lone pairs and 2 electrons in the pi bond. So I have 6 pi electrons. If I solve for n, it turns out to be 1. It's not a fraction. The thing is, the structure is cyclic, it's a ring, it's conjugated. I can draw resonances clockwise, counterclockwise throughout the structure, throughout the carbons of the structure, and it's planar because I have throughout sp2 hybridization of the carbon centers, so it qualifies all the rules. It's aromatic. Next is this guy. So again, that's an sp2 center. I expect it to be trigonal planar, that area of the ring, and I can draw resonances either this way or the other way, whichever way I want. So it's fully conjugated and it's planar, and now we test for 4n plus 2 rule equals to number of pi electrons. So 4n plus 2 is going to be equal to 2 pi electrons. So 4n equals to 2 minus 2 equals to 0. 4n equals to 0. N must be equal to 0. It's not a fraction, so it's acceptable. Remember, we just always need to be n to be 0, 1, 2, any whole number, but not a fraction. So this guy is aromatic. That structure is aromatic. Okay, now here I have lone pairs that I can push resonances, which will affect, of course, the other pi bonds. I can push also this way. So this molecule is completely conjugated because I can push this one here and that will go there, and you keep going round. So all carbon atoms will play part in resonance, and because the lone pairs can be used for resonance, I do have 6 pi electrons in the 3 pi bonds, and I have the 4 electrons in the 2 lone pairs. 6 plus 4 gives me 10 pi electrons. Let's test that for the last rule and solve for n. So in this case, 4n is going to be equal to 10 minus 2, which is 8. N solves for 2, it's not a fraction. I check it. Now you have a hydrogen there, you have a hydrogen here. This carbon center is sp2. That carbon center is also sp2. The molecule is predicted to be aromatic. Okay, so what you have here is what we call the porphyrin ring. You see this in heme. Part of the hemoglobin is the protestic group. In the hemoglobin, you learn that in biochemistry. Protestic groups are non-protein organic structures in an enzyme, for example. So the path in red is where the electrons are highly conjugated. So if you count, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So you do have 18 pi electrons, and testing that for 4n plus 2 rule, you get 4n equals to 16, n equals to 4. Of course, it's a ring, there is a path that's highly conjugated. These double bonds don't take part in resonance, so we don't count them. Okay, so that's what makes your blood, this general structure is what makes your blood red whenever iron is sitting in there, or it's gonna make chlorophyll green whenever magnesium is sitting in there in plants. Okay, so I hope that helps. Practice, replay the video, know how to determine which molecule is enter-aromatic, which one is non-aromatic, and we'll do more examples in class on tomorrow, Tuesday, April the 28th.